High-temperature sulfidic or naphthenic acid corrosion, understanding corrosion challenges in extreme heat conditions. High-temperature sulfidic or naphthenic acid corrosion, NAC, is a critical issue in oil refining processes, particularly in units operating at elevated temperatures. This form of corrosion occurs when sulfur compounds and naphthenic acids in crude oil attack metal surfaces at temperatures typically above 200 degrees Celsius or 400 degrees Fahrenheit. The phenomenon is complex because sulfur can form protective iron sulfide scales on steel surfaces, but these scales can be disrupted by high concentrations of naphthenic acids or by turbulent flow conditions. NAC leads to significant metal loss, especially in areas with high fluid velocities such as elbows, valves, and transfer lines. The consequences include equipment failure, unplanned shutdowns, and costly repairs, making it essential for refineries to understand and manage this corrosion mechanism effectively. The interplay between sulfur and naphthenic acids, combined with operational variables like temperature and shear stress, requires a comprehensive approach to material selection, crude blending, and process control to mitigate risks. NAC typically occurs at temperatures above 200 degrees Celsius or 400 degrees Fahrenheit and becomes more aggressive as temperatures rise toward 400 degrees Celsius or 750 degrees Fahrenheit. The primary corrosive agents are sulfur compounds, such as hydrogen sulfide or H2S, and naphthenic acids or NAs present in crude oil. Sulfur compounds tend to form protective iron sulfide or FES scales on steel surfaces, which can reduce corrosion rates. However, naphthenic acids interfere with this protective mechanism by breaking down or preventing the formation of these scales, leading to accelerated metal loss. The severity of NAC depends on several variables, including the concentration of naphthenic acids, measured by total acid number or TN, sulfur content, operating temperature, and fluid velocity. High shear stress zones, such as bends and valves, are particularly vulnerable because turbulent flow can strip away protective scales, exposing fresh metal to corrosive attack. Understanding these factors is crucial for predicting corrosion behavior and implementing effective mitigation strategies. The severity of NAC is influenced by multiple operational and chemical variables. High TN values indicate elevated naphthenic acid concentrations, which significantly increase corrosion risk. Similarly, sulfur content plays a dual role. While moderate sulfur levels can help form protective sulfide scales, excessive sulfur combined with high TN can lead to mixed corrosion mechanisms. Temperature is another critical factor, as corrosion rates escalate with increasing heat. Fluid velocity and shear stress are equally important because they determine whether protective scales remain intact or are eroded away. Equipment most commonly affected includes crude and vacuum distillation units, transfer lines, side-cut piping, and areas with complex flow patterns. These components often experience localized thinning, pitting, and even catastrophic failures if corrosion is not adequately controlled. Regular inspection and monitoring of these high-risk zones are essential to prevent unexpected outages and maintain operational integrity. Effective mitigation of NAC requires a multifaceted approach. Material selection is a primary defense, with stainless steels and chromium molybdenum (CRMO) alloys offering superior resistance due to their ability to form stable sulfide scales. Crude management is another critical strategy. Blending high-TN crudes with lower acid oils can reduce overall corrosivity, while controlling sulfur levels helps maintain protective scale formation. Chemical corrosion inhibitors can provide additional protection, although their effectiveness varies depending on operating conditions and fluid composition. Process control measures, such as optimizing temperature profiles and managing flow velocities, are essential to minimize shear stress and prevent scale removal. Implementing these strategies in combination ensures a robust defense against NAC, reducing the likelihood of equipment failure and extending the service life of critical refinery components. NAC can be categorized into three main types based on the interaction between naphthenic acids and sulfur compounds. Type 1, or pure NAC, occurs primarily in low-sulfur crudes where naphthenic acids directly attack metal surfaces without interference from sulfide scales. Type 2, or mixed NAC and sulfidation, is the most common scenario in sulfur-containing crudes, where both mechanisms contribute to corrosion. Type 3, or NAC inhibited by H2S, occurs when high concentrations of hydrogen sulfide promote the formation of protective sulfide scales, reducing the impact of naphthenic acids. Understanding these classifications helps refineries tailor mitigation strategies to specific crude blends and operating conditions, ensuring optimal protection against corrosion. High-temperature sulfidic/naphthenic acid corrosion poses significant challenges in oil refining, particularly in units operating at elevated temperatures with high TAN crudes. The interplay between sulfur compounds and naphthenic acids creates a dynamic corrosion environment that requires careful management. Key mitigation strategies include selecting corrosion-resistant materials, blending crudes to control TAN and sulfur levels, applying chemical inhibitors, and optimizing process conditions to minimize shear stress and maintain protective scales. Regular monitoring and inspection of high-risk areas are essential to detect early signs of corrosion and prevent catastrophic failures. By implementing these best practices, refineries can enhance equipment reliability, reduce maintenance costs, and ensure safe and efficient operations.